Hello there. This video program is designed to train operating personnel in the principles and practices of modern utility operation. Now, we assume that everyone taking this course already has some technical experience and familiarity with electrical theory. But in order to make sure that you all begin the program with the same background knowledge, this topic is devoted to a review of electrical fundamentals. Now, because this is a review, we will move along quite fast. Although many of you will be familiar with this material, stick with us. It's going to get more interesting and more complicated. In this review, we will discuss methods of voltage generation, current flow, electrical properties of resistance, inductance and capacitance, power, power factor, three-phase operation of power systems, voltage drop, and so on. So let's go over to the office and join Margaret there.
Okay, let's begin our review of fundamentals by taking a brief look at a simple electrical circuit. This is a battery whose function in the circuit is to force electrons around the circuit like this. The stronger the battery, the more electrons are forced around the circuit each second. The strength of the battery is measured in volts. In this case, 20 volts. Voltage is represented by V, or E, where E stands for electromotive force. Changing to 40 volts will force more electrons around this circuit than 20 volts did. The flow of electrons is called current and is measured in amperes. Current is represented by the symbol I. If I is, say, 4 amperes, then there are twice as many electrons per second moving around this circuit than if I is 2 amperes. The load in this circuit is, let's say, a heater, and it provides resistance to the flow of current. This resistance is measured in ohms and is symbolized by the letter R. It is twice as difficult to force electrons through a 10 ohm resistance as through a 5 ohm resistance. Volts V, ohms R, and amperes I are related in the following manner. I equals V divided by R, which is known as Ohm's law. This means that in our circuit, if the heater has a resistance of 3 ohms and a voltage of 6 volts is applied, then the current flow would be I equals V over R, which equals 6 over 3, which equals 2 amperes. You can see that if V is doubled to 12 volts, then I will also double to 4 amps. This can be calculated by I equals 12 volts divided by 3 ohms, which equals 4 amps. Remember, the resistance of the circuit is kept constant at 3 ohms. But if we now insert another identical heater in series, we double the resistance from 3 to 6 ohms. Then current will equal 12 volts divided by 6 ohms, which equals 2 amps. Therefore, doubling the resistance and keeping the voltage constant cuts current in half. Ohm's law, I equals V over R, can be rearranged as V equals I times R, or R equals V divided by I. We can easily remember Ohm's law from this diagram. Just cover up the term you want to find, then V equals I equals and R equals. In this circuit, we've been discussing direct current, or DC. In DC circuits, current flows in one direction only. So, what have we learned so far? Well, if we wish to increase current, we must 1. Increase the voltage, or 2. We can decrease the resistance of the circuit, or 3. We can do both. Remember, V is voltage in volts, which forces current to flow in the circuit. I is current flow in amperes, which is really a measure of how many electrons per second are flowing in the circuit. And R is the resistance of the circuit to current flow and is measured in ohms. It is often important to know how fast a load is consuming energy. The rate at which energy is consumed is called power and is measured in watts. That is, power is equal to energy divided by time. 1 watt is equivalent to consuming 1 joule of energy in 1 second. Power in watts can be calculated using the following formulas. Power equals current times voltage. Power equals current squared times resistance. Or power equals voltage squared divided by resistance. In our first example, the voltage applied was 12 volts and circuit resistance was 6 ohms, which gave us a current of 2 amperes. Power can be calculated by multiplying current times voltage, or power equals 2 amperes times 12 volts, which is 24 watts. This means that the load is consuming energy at the rate of 24 joules per second from the battery. This is equivalent to consuming 24 watts of power. Remember, power is the rate at which energy is consumed. If we wish to determine the total energy consumed, we must multiply the power by the time period involved. In our circuit, if we wish to know how much energy is consumed by the load in 12 hours, we multiply 24 joules per second by the number of seconds in 12 hours. Well, 12 hours times 60 minutes per hour times 60 seconds per minute, this works out to be 43,200 seconds. Therefore, energy is equal to 24 joules per second times 43,200 seconds. This works out to be energy is equal to 1,036,800 joules. As you can see, the joule is a very small unit, so energy is usually measured in watt-hours or kilowatt-hours. In this case, we would simply take 24 watts times 12 hours to get an energy consumption of 288 watt-hours. The kilowatt-hour is 1,000 watt-hours, and the megawatt-hour is 1,000,000 watt-hours, or 1,000 kilowatt-hours. It is important to distinguish between power in watts and energy in watt-hours. Again, power is the time rate of consuming energy and is equal to energy divided by time, while the total amount of energy used over a period of time represents the actual work done by the circuit. In our example, the circuit power consumed could also have been calculated using P equals V squared over R, which is equal to 12 volts squared divided by 6 ohms, which works out to be 24 watts, or P equals I squared times R, which equals 2 amps squared times 6 ohms, which works out to be 24 watts. In each case, the results are identical. Power consumed is equal to 24 watts. Right, now let's take a short break to go through the problems in our workbooks. When we return, we will be looking at some commonly used methods for generating voltage. There are several commonly used methods for generating voltage. One method is friction. By rubbing certain materials together, the electrons move from one material to the other, thus producing a voltage. A second method is pressure. By squeezing the crystals of certain substances together, voltage is produced. A third way is heat. By heating the junction where two unlike metals are joined together, voltage is generated. A thermocouple, used for measuring temperatures, is an example of this. A fourth way is by light. When light strikes photosensitive substances, voltage is produced. This is known as photoelectricity. A fifth way is by chemical action. Batteries are an example of the generation of voltage by chemical reactions. However, the most common method of generating electricity is by moving a conductor through a magnetic field. What is a magnetic field? Well, we all know that a magnetic field is present around a permanent magnet. These lines, called magnetic lines of force, show the nature of the field around the magnet. The lines of force are concentrated at these two ends, or poles. And by convention, they leave the North Pole and enter the South Pole. Now let's bend this bar magnet as shown in this diagram. You can see that the lines of force are concentrated as they pass directly between the poles. When a wire is moved through this magnetic field, a voltage is produced. Actually, what is happening is that the wire is cutting the magnetic lines of force surrounding the magnet. This produces an electromotive force, or voltage, across the terminals of the conductor. When the circuit is completed, this voltage will cause electrons in the wire to move, and, consequently, current will flow. When the conductor is moved in the opposite direction, the voltage develops in the opposite direction, and also current will flow in the opposite direction. Let's now place a coil of wire between the poles of a magnet and cause this coil to rotate. Notice that we have connected a voltmeter to measure the voltage, that is, the electromotive force, between the two ends of the wire. The magnetic lines of force, sometimes called flux, are shown here. As we see here, the rotation of the coil of wire between the poles of the magnet will produce voltage. This graph shows the variation of voltage with time. The vertical axis represents the magnitude of the voltage, while the horizontal axis represents the passage of time. For convenience, we will calibrate the time axis in degrees of coil rotation. One complete rotation of the coil will correspond to 360 degrees on our angular scale. Having stopped the action at 0 degrees, as shown here, let us analyze just how this voltage is generated. At 0 degrees, the coil is moving parallel to the lines of force, so it is not cutting any lines of force. Therefore, the voltage generated is 0. After a 90-degree rotation, when the coil is here, it is moving directly across the lines of force and is cutting them at the maximum rate. Therefore, voltage is at a maximum. When the coil has rotated another 90 degrees, again, it is not cutting any lines of force, and voltage is again 0. After a still further 90-degree rotation of the coil is cutting lines of force at a maximum rate, but in the opposite direction. Maximum voltage is therefore induced in the opposite direction. And after another 90 degrees, we are back at our starting point, and voltage is 0. On this graph, we have shown 2 complete cycles of voltage, corresponding to 2 complete rotations of the coil. Note that the magnitude of the voltage alternates first in the positive and then in the negative direction. The number of complete revolutions of the coil in 1 second is the frequency and is measured in cycles per second, or hertz. Let's assume that it took 1 second for the coil to make 2 complete rotations. Then the frequency is 2 cycles per second. The time it takes for 1 complete cycle is called the period and is equal to 1 divided by frequency. In our example, the time to complete a full cycle is 1 divided by 2, or half a second, as shown here. Electrical systems are usually operated at a frequency of 50 or 60 cycles per second. There is limited use at 25 cycles per second, such as for electric railroads. The hertz is the accepted measure of system frequency and is equal to 1 cycle per second. Therefore, a frequency of 60 hertz means that the wave has oscillated through 60 complete cycles in 1 second. A 60 hertz wave will complete 1 cycle in 1 divided by 60 seconds. This is 0.0167 seconds, or 16.7 milliseconds. And this is the period of the wave. In power systems, it is essential that all generating units run at the same electrical frequency. This is called synchronism, and we will talk more about how generators are synchronized later in the program. Now, the current that flows when the coil is connected to a load will also alternate. This is called alternating current, or AC. Let's take a closer look at this. This load, an electric lamp for example, is connected to an AC voltage supply. When the voltage is 0, current is 0. When AC voltage is in its positive half cycle, current in the circuit will flow this way. When the AC voltage is in its negative half cycle, the current will be reversed, and so on. Now let's take a short break to go through our workbooks. As we have just seen, the value of an AC voltage varies continuously. So, how do we specify its value? Sometimes it is 0, sometimes maximum, and sometimes in between. We could call it by its peak value, say 100 volts, peak, but we must remember to say peak. A more common method is to use the effective or RMS value. An RMS voltage effects the same amount of work as a DC voltage of the same magnitude. It is calculated by dividing the peak voltage by the square root of 2. This is the same as multiplying it by 0.707. When an AC voltage is applied to a pure resistance, an AC current flows. In this circuit, when voltage is peak, current is also peak. When voltage is 0, current is 0. In other words, the current and voltage fluctuate together and are said to be in phase in a purely resistive circuit. The RMS, or effective current, is the value of current that has the same heating effect as a DC current of the same magnitude. It is calculated in a manner similar to voltage. That is, by taking the peak current and dividing it by the square root of 2, or multiplying it by 0.707. Okay, unless otherwise specified, AC current and voltage are always given in RMS quantities. For most practical work, the RMS values are really more useful than instantaneous or maximum values. Most common types of measuring instruments are calibrated to read RMS values. Again, all values of AC current and voltage are specified in RMS unless otherwise stated. So, we have just looked at alternating voltage and current in a resistive circuit. It may be natural to ask, how can power be delivered to this circuit when voltage and current are continuously changing direction? As with the case of the DC circuit, power delivered is simply the product of voltage and current. In the AC case, it is the voltage times current at any instant of time. Let's look at this graphically by drawing a curve for power. At the beginning of the cycle, 0 volts times 0 amps gives us 0 watts. After 1/4 cycle, or 90 degrees, has passed, peak current times peak voltage gives us peak power. After another 1/4 cycle, power is again 0. But what happens here, in the negative half cycle of voltage and current? As you know, when two negative numbers are multiplied together, the result is a positive number. Therefore, even though the voltage and current are both negative, their product is positive power in watts. So, at this point, maximum negative voltage and current gives maximum positive power. Power is therefore a sine wave, oscillating about this axis. But we are really interested in the average value of this power wave, since the average power determines the energy that will be consumed by this circuit. It turns out that the average value of this power wave is equal to the peak value divided by 2. This is obvious, since the power wave above this axis is exactly the same as the power wave below the axis. Therefore, the average value over a complete cycle is here and equals P max divided by 2. Let's put some numbers on our diagram. Assume our voltage supply is 100 volts peak, which is 100 times 0.707, and this equals 70.7 volts RMS. Let's also say resistance is 5 ohms. By Ohm's law, peak current is voltage peak divided by resistance, which equals 100 volts divided by 5 ohms, and this is 20 amps peak. RMS current could also be calculated using RMS voltage. RMS voltage divided by resistance is equal to 70.7 volts divided by 5 ohms, which equals 14.14 amps RMS. Let's now see what the peak value of the power wave is. The peak value of power is simply the peak voltage times peak current, which equals 100 volts times 20 amps, and this is 2,000 watts. What is the average power over the cycle? As we just saw, average power equals power max divided by 2, which is 1,000 watts. But look what happens when we multiply RMS voltage by RMS current. 70.7 volts times 14.14 amps equals 1,000 watts of power, the same value as we just calculated. Therefore, the average or effective power in a resistive circuit is simply the product of RMS voltage and RMS current. In fact, in a resistive circuit, all the formulas for power we looked at for DC also apply for AC. Power equals voltage times current, power equals current squared times resistance, and power equals voltage squared divided by resistance, where in these formulas P is the effective power, V is the RMS voltage, I is the RMS current, and R is the resistance. At this point, we'll take a short break to work through the problems in our workbooks. Ted Major will be back after the break to discuss voltage and current waveforms in inductive and capacitive circuits.
Thank you, Margaret. Now, as you remember from the last segment, voltage and current in a resistive circuit are in phase. They reach their maximum and minimum values at the same time. Let's now look at the effect of inductance and capacitance in an AC circuit. First, inductance. Now, inductance is the electrical property of a circuit which opposes any changing current. If an AC voltage is applied to a pure inductor, the resultant current reaches its maximum and minimum values after the voltage has passed those values. The current is said to lag the voltage by 90 degrees. This 90 degrees is called the phase angle between voltage and current. The voltage and current are out of phase by 90 degrees. A more convenient way of comparing phase angles is by drawing a vector diagram like this. The vector is a line which shows magnitude, that is how much, and it also shows direction. This vector represents the voltage. Its length is proportional to the RMS value of voltage. The current in the inductive circuit is represented by this vector, and as you can see, it is drawn lagging, that is 90 degrees with respect to the voltage. its length is proportional to the RMS value of current. In order to provide a convenient reference for comparing other voltages and currents, the voltage vector is often drawn at 0 degrees, as we show here. Now, in a resistive circuit, the resistance indicated by R is actually the opposition to current flow. In an inductive circuit, the opposition to current flow is called inductive reactance, and its symbol is X sub L. Its value depends upon the actual inductance of the circuit, and this value is measured and indicated in ohms. The RMS value of current in a purely inductive circuit can be calculated simply by dividing the RMS voltage, V, by the value of inductive reactance, X sub L. The resultant current, I, will of course be out of phase with the voltage by 90 degrees, as shown on this vector diagram. Okay, so that is inductive current. Let us now consider power in the inductive circuit. Let's return now to our voltage and current waveforms, and we will multiply the instantaneous values to find power, just like we did earlier with the resistive circuit. The first thing to notice is that whenever the current or voltage is 0, then their product, power, will be 0. So power is 0 here, at this point, and here, and so on. Now, when current and voltage are both positive, or even both negative, then their product, power, will be positive. You remember, multiplying two negative values together results in a positive. But whenever the voltage and current have different signs, a positive times a negative, then their product is negative, as we see here. So, this then is the resulting power wave for a circuit consisting of inductance only. Be sure to notice that the voltage and current are out of phase, so the power curve has a negative component. This is unlike the case with pure resistance, where power was always positive. For a pure inductor, we have as much negative power as positive. This means that power is being delivered to the inductor in a quarter cycle, and it is returned in the next quarter cycle. Therefore, the average power consumed over the cycle is 0. Pure inductors actually consume no energy, but alternately store it in a magnetic field and then return it to the circuit. Therefore, the product of voltage and current cannot be called active power, as it does no active work. So we give it the name reactive power, or volt-amperes reactive. This is abbreviated as VAR, or simply VARS. Let's look at this on a vector diagram. By convention, active power is drawn at 0 degrees. We can represent inductive VARs on a vector diagram like so. The inductive VARs are drawn at an angle of 90 degrees with respect to active power. The length of the vector is proportional to RMS voltage times RMS current. These inductive VARs are known as positive VARs. After all, the generator does have to produce them. So, that is the effect of inductance. Let us now look at a circuit containing capacitance only. When an AC voltage is applied to a capacitor, the opposite situation to the inductor results. The current reaches its maximum and minimum values 90 degrees before the voltage. So the current is said to lead the voltage by 90 degrees. In the vector diagram, the capacitive current is shown leading 90 degrees with respect to the voltage. How much current flows? Again, it depends on the amount of opposition to current flow in the circuit. In a capacitor, opposition to current flow is called capacitive reactance, and it is indicated by the symbol X sub C. And this is measured in ohms. RMS current will be equal to the RMS voltage divided by the capacitive reactance, X sub C. But what is the value of power in this pure capacitive circuit? As before, the power curve is obtained by multiplying the instantaneous values of voltage and current. And we find that the average power consumed is 0. In this case, energy is being stored in the electric field for 1/4 cycle and returned to the circuit in the next quarter cycle. Since the average power is 0, power in a capacitive circuit is also called volt-amperes reactive and is measured in VARS. Capacitive VARS are in the opposite direction to inductive VARS. This is because the current is leading instead of lagging. Capacitive VARS are represented on the vector diagram at an angle of minus 90 degrees to real power. And by convention, these are given the negative sign and called negative VARS. Obviously, if a circuit contains both capacitance and inductance, the positive and negative VARs tend to cancel each other out. In fact, energy moves between the magnetic field of the inductor and the electric field of the capacitor. In this example shown here, capacitive VARs are lower in magnitude than the inductive VARs. The sum total is that less VARs need to be supplied by the generator to this circuit. Right, now let's stop for a moment to summarize what we have covered so far. First, opposition to current flow in a resistor is resistance, R. In an inductance, it is inductive reactance, X sub L. And in a capacitance, it is capacitive reactance, X sub C. In a resistive circuit, the current through the resistor is in phase with the voltage. We can draw the vector diagram like so. In an inductive circuit, the current lags the voltage by 90 degrees. This vector diagram illustrates the phase relationship. In a capacitive circuit, the current leads the voltage by 90 degrees, and here is its vector representation. A resistor absorbs active power. This is sometimes called true power or real power, and it is measured in watts. Inductors and capacitors do not consume any energy. Energy is received in part of the cycle and given back in another part of the cycle. Inductive and capacitive volt-amperes are called VARs. In a purely resistive circuit, active power in watts is placed on the vector diagram at 0 degrees. In a purely inductive circuit, VARs are said to be positive, and in a purely capacitive circuit, VARs are negative. Okay, we have covered a lot of material, so at this time, I think it's time we had a break. Switch off the tape now and thoroughly go through the examples in your workbook. So, now we know the effects of pure resistance, inductance, and capacitance. So, let's now look at an example where we have a circuit containing all three quantities. We will start with resistance and then add the other circuit components in parallel as we proceed. We have a voltage of 100 volts. The resistance is 2.5 ohms, and ohms are usually represented by the Greek letter omega. So that will give us a value of current through the resistance of 40 amperes. So what is the power absorbed by this resistive circuit? Well, by simply multiplying the current by the voltage, that is 40 amps times 100 volts, we find that the active power is equal to 4,000 watts. That is 4 kilowatts. We can start our vector diagram with this value. Active power equals 4 kilowatts. Now let's see how much current we have flowing through the inductive circuit. The inductive reactance is 2.5 ohms. Therefore, the inductive current is 40 amperes, and this will be lagging the voltage by 90 degrees. You will also remember that in this purely inductive circuit, the active power consumed will be 0. Instead, we must supply positive VARS to the circuit. The total VAR requirement is given by multiplying the current and voltage. That is 40 amperes times 100 volts. That equals 4,000 VARs. That is 4 kilovars. So we can now represent this on our vector diagram as a positive demand for VARs. Now let's add a third circuit, this time of pure capacitance. The capacitive reactance has a value of 10 ohms, and therefore the capacitive current in this circuit will be 10 amperes. The resulting negative VARs in this circuit will be equal to 10 amperes times 100 volts, and that equals 1 kilovar. But remember, these VARs in the capacitive circuit are flowing in the opposite direction to those in the inductive circuit. They are known as negative VARs and are shown on the vector diagram like this. This capacitive circuit acts as a compensation for the inductive circuit and actually reduces the total quantity of positive VARs required. The result is that only 3 kilovars need to be supplied to the circuit from the generator. The other 1 kilovar is supplied by the capacitance. Now if we put a voltmeter and an ammeter in the main circuit like this, what would these instruments indicate? Well, of course, the voltmeter would read the same value, that is the 100 volts, that is across each of the elements of the circuit. But the ammeter would read a combination, that is the sum of the resistive, inductive, and capacitive currents. As these three currents are out of phase with each other, they cannot be added arithmetically, but they must be added as vectors. As a matter of fact, if we complete the power triangle, that is by adding vectorially the active power, which is volts times active current, and the reactive power, which is volts times reactive current, we will come up with the value which is volts times combined current. The combined current is that which is indicated by the ammeter here. This value is known as volt amperes, or kVA. But how can we find the value of this other than by direct measurement? Well, you probably remember the Pythagoras theorem, which says that the square of the hypotenuse is equal to the sum of the squares of the two sides on a right angled triangle. This means that volt-ampere squared will be equal to watts squared plus VARS squared. And in our example, this will come to 4 squared plus 3 squared. If you work that out, that equals 25. And therefore, the magnitude of volt-amperes will be the square root of 25. And that comes to 5 kVA. Right, let's look at the power triangle again. Here we have active power, reactive power, and VA, volt-amperes. This is known as volt-amperes, VA, since it is the product of total voltage and total current. Thinking back to our resistive circuit for a moment, you will remember that the voltage times the current measured the power being absorbed. So one could perhaps be forgiven for thinking that the volt-amperes is an indication of the power being absorbed by this circuit. For this reason, VA is often called apparent power. It is not the true active power. The true active power is indicated by this vector, which is the power absorbed in the resistive circuit. We have already seen that VARs do not absorb any active power. The ratio active power divided by apparent power is known as the power factor. And this is a measure of the useful or real true power portion of volt-amperes. Another way of arriving at the value for power factor is by observing the power triangle we have just constructed. Remembering your trigonometry, you can see that the active power divided by the volt-amperes is equal to the cosine of this angle, which we will call theta. Therefore, we can say that the power factor equals cosine theta. As a matter of fact, the magnitude of this angle theta is the same as the angle by which the total current and voltage are out of phase. So, what is the power factor in our example? Well, the power factor equals the true power, 4,000 watts, divided by the apparent power, 5,000 volt-amperes, and this comes to 0.8. Now, since this is also the cosine of the angle, we can look in our trigonometric tables to discover that where the cosine is 0.8, then this angle will be 37 degrees. What does 0.8 power factor tell us? Well, we can say that 80% of the apparent power is the real power in watts. In a circuit that has equal inductive and capacitive VARs, the volt-amperes consist entirely of watts. The power factor in this case is equal to 1, since watts divided by volt-amperes will equal 1. This is known as unity power factor. The sum of inductive and capacitive VARs is then 0. In a circuit that has no resistance at all, then active power is 0 and volt-amperes consist entirely of VARs. In this case, the power factor will be 0 as there are no watts flowing. Circuits that have a combination of watts and VARs have power factors somewhere between 0 and unity, and this is, of course, the most usual case. There is a power factor associated with every point in the power system. Thus, we can talk about the power factor at the generator, or the power factor at the load, or the power factor anywhere else in the system. Power factors are usually kept as close to unity as possible. And why is this? Well, we want to supply as much active power, watts, to the load as possible. After all, it is the active power that does work for us. Reactive power, on the other hand, does no work for us. It does not consume energy, but it is necessary to supply VARS so as to set up the magnetic fields in the system. Therefore, VARS do serve a very vital function and are necessary to the operation of the system. But the generator has to supply these VARS, and this has the effect of limiting the amount of megawatts that can be supplied from the generator. For example, let's look at a generator rated 100 MVA. This would be able to supply 100 megawatts were there no megavar demand in the system. In this situation, the power factor will be unity, and megawatts will equal MVA, and that will equal 100 megawatt, as we can see here. But suppose now we assume an inductive load power factor of 0.9. The power triangle will look like this. The generator output of active power in watts will now be limited to the quantity represented by this vector. Active power will equal the power factor times the apparent power, and this is 0.9 times 100 MVA, and that will come to 90 megawatts. Let's now calculate the reactive power requirement. MVA squared equals megawatts squared plus megavars squared. And in our example, we see that 100 squared equals 90 squared plus megavars squared. So the reactive power supplied will be the square root of 100 squared minus 90 squared. If you work this out, it comes to 43.6 megavars. The machine can only generate 90 megawatts in addition to the required megavars. You can see that megavar production makes it necessary to build machines larger than would be necessary if no VARs were required. To recap, let's look at the power triangle. The active power in megawatt is a measure of how fast the load is consuming energy. Power is consumed in the process of doing work. This energy is consumed by the load, and this is what we pay the power company for. To produce this energy, we must provide fuel input to the turbine driving the generator. VARs are a measure of how much energy is required to set up electric and magnetic fields. These VARs oscillate between the fields and the power supply. Thus, VARs require no energy. Inductive VARs are positive and capacitive VARs are negative. The ratio of active power divided by apparent power is called the power factor. That value, power factor, is trigonometrically speaking the cosine of this angle, theta. The value of any one of the sides of the triangle can be calculated from the equation volt-amperes squared equals watts squared plus VARs squared. While on this subject of power, let us talk for a moment about the difference between power and energy. Electric power is measured in kilowatt, and energy is measured in kilowatt hours. For example, if a load consumes 2 kilowatt for 2 hours, then the energy used by the load is 4 kilowatt hour. Electric utility companies usually bill their customers in terms of the energy used, that is in kilowatt hour. Let us consider a generator supplying 600 megawatt to the system. After 30 minutes, this generator has provided 300 megawatt hour. After 1 hour, it has provided 600 megawatt hour, and after 10 hours, it has supplied 6,000 megawatt hour. Right, now I think we all deserve a break. Go through the examples in your workbook carefully and thoroughly.